Centuries ago, Europe was gripped by a silent catastrophe. This was the era of the medieval years of famine, a time of profound crisis, often overshadowed by the Black Death, but equally devastating. Historical texts from the period are sparse and vague, leaving a haunting mystery in their wake. What force could cause such widespread and repeated famine, collapsing societies and reshaping history? The answers were not lost, merely locked away in nature's own vaults. Hidden within ancient trees and deep polar ice are precise records, a scientific narrative waiting to be read. These natural archives, tree rings and ice cores, act as silent witnesses to the past. By learning to decode their language, we can finally solve this ancient puzzle. You will gain a completely new framework for understanding how climate and human destiny are intertwined. What did these forgotten archives reveal about the true cause of the famines? And how does this discovery force us to rethink medieval life entirely? We are about to trace the evidence step by step, from a volcanic trigger to a cascade of failure. What does it mean for a civilization to be at the mercy of the sky? Think of a tree as a patient, meticulous scribe. Each year, it adds a single new ring beneath its bark, a diary entry written in wood. In a good year, with ample warmth and gentle rains, the tree grows robustly, producing a wide, pale band of early wood. When summer arrives, growth slows, forming a denser, darker late wood. Together, these two bands form one annual ring, a record of that single growing season. A narrow, cramped ring tells a story of struggle, perhaps a cold snap or a relentless drought that stifled growth. This science of reading these wooden chronicles is called dendrochronology. By comparing patterns of wide and narrow rings across living trees, ancient timbers, and even fossilized wood, scientists can build continuous calendars stretching back thousands of years. These rings give us a regional report card, telling us precisely what the weather was like in a forest in a specific year with stunning accuracy. Now travel to the polar ice caps. Here, another kind of archive accumulates, layer upon imperceptible layer with each winter's snowfall. Over centuries, this snow compresses into solid ice, trapping tiny bubbles of ancient atmosphere within it. Drilling deep into this ice is like turning back the pages of Earth's own climate logbook. Each core, a cylinder of frozen history, contains clues locked in the ice itself. The chemical composition of the water molecules can tell us the temperature of the ocean when the snow originally evaporated. Those trapped air bubbles are direct samples of the ancient atmosphere, allowing us to measure past levels of gases like carbon dioxide. And perhaps most crucially for our medieval mystery, volcanic eruptions leave a distinct fingerprint. When a volcano explodes with enough force, it blasts millions of tons of ash and sulfur gases high into the stratosphere. This ash, called tephra, can fall on ice sheets, creating a visible, datable layer. The sulfur gases transform into reflective aerosols that circle the globe, and these too are preserved in the ice. So we have two witnesses. The tree ring offers an intimate, local testimony. It tells us if a particular summer in the Alps or in England was kind or cruel to life. The ice core provides the bigger picture, the global context. It reveals what was happening in the planet's atmosphere that could have caused those local hardships. Written chronicles from the Middle Ages tell us the terrifying that famine gripped the land, but these natural archives hold the key to the why. They work in tandem, one filling in the details the other might miss, to reconstruct a world we thought was lost to time. What they would eventually reveal was not a simple story of bad weather, but a precise chain of atmospheric chaos. By the dawn of the 1300s, Europe was a society living on a knife's edge. For generations, a warmer climate and relative peace had allowed its population to swell, a testament to human resilience and agricultural ingenuity. Forests were cleared, marshes were drained, and farms crept up hillsides and into valleys once considered too poor or too remote for reliable harvests. This expansion created a fragile prosperity, a civilization balanced precariously on lands that could barely support it in the best of times. The margin for error had become vanishingly thin. A single failed harvest could mean hardship, two could spark a local crisis, but three or more in succession would break the entire system. This was the human landscape, a network of communities deeply interconnected and deeply vulnerable. Then the weather turned. Historical records from across the continent begin to speak of a catastrophe, a period known to us as the Great Famine, stretching from 1315 to 1317. Chronicles describe relentless, cold rains that rotted seeds in the ground, summers that never truly arrived, and a desperate scarcity that reshaped society. For centuries, these texts were our only window into the suffering, telling us the what but leaving the crucial why shrouded in mystery. What kind of shock could possibly be severe enough and widespread enough to cripple an entire continent's food supply for years on end? The human system was clearly primed for collapse, but it awaited a trigger. The silent testimony of the ice cores would finally point a finger at the culprit. Leading researchers began to assemble a compelling hypothesis, one that identified a volcanic trigger as the starter pistol for the entire crisis. The evidence was locked in those frozen layers in the form of microscopic sulfate aerosols. When a volcano erupts with colossal force, it does more than just spew lava and ash. It propels millions of tons of sulfur dioxide gas high into the stratosphere. Up there, the gas transforms into a reflective haze of tiny particles. These aerosols act like a global sunshade, scattering incoming sunlight back into space and causing the planet's surface to cool and rapidly. This isn't a gradual climate shift, it's a sudden atmospheric shock. The ice cores serve as the perfect archive for this phenomenon because each snowfall captures and preserves a sample of that polluted sky, creating a datable chemical signature for every major eruption. And the cores from this pivotal era tell a startling story of repeated violence from the Earth itself. One of the most significant signals corresponds to a titanic event around the year 1257, now linked to the eruption of the Samalas volcano in Indonesia, an event thought to be one of the largest of the last 10,000 years. But the assault didn't stop there. The ice records suggest a cluster of other major eruptions followed in the late 1300s, a period of exceptional volcanic unrest. Imagine the cumulative effect. Just as societies were reaching their peak vulnerability, the planet's thermostat was being turned down not once but several times in succession. This global cooling would have fundamentally rewritten regional weather patterns. Jet streams could have been displaced, growing seasons abruptly shortened, and the delicate balance of precipitation completely upended. Gentle spring rains might have been replaced by relentless, crop-drowning downpours, while summer warmth essential for grain to ripen simply failed to arrive. The stage was now set, the atmospheric conditions primed for disaster. But how exactly did this distant volcanic winter translate into empty fields and empty stomachs across medieval Europe? The evidence was no longer just a chemical signature trapped in polar ice. It was etched into the very wood of ancient trees. Dendrochronologists, acting as historians of the forest, began to trace the physical impact of those volcanic eruptions. Their findings painted a stark picture of environmental shock. Following the major eruption signals in the ice, tree ring chronologies from across Europe and the Northern Hemisphere tell a remarkably consistent story. The rings for the years after these events are not just narrow, they are often extraordinarily dense and tightly packed. This is the fingerprint of a year without a summer. When temperatures plummet and the growing season is brutally shortened, a tree cannot produce its normal, wide band of springwood. Instead, It spends most of the brief, cool summer producing only the hard, dense late wood, resulting in a ring that is both thin and dark. It is a record of survival, not prosperity. In the ancient oaks of Britain, meticulously studied from cathedral roofs and preserved bogs, the rings for the early 1300s show this exact pattern of severe stress. The same story is told by the pines of Scandinavia, trees that have endured for centuries on mountain slopes. Their growth, year by year, fell into near synchrony with the oaks a continent away, all of them recording the same atmospheric chill. This network of wooden sentinels confirms the ice core hypothesis with breathtaking clarity. The volcanic eruptions did not just create a theoretical cooling, they triggered a tangible, widespread, and synchronous environmental crisis. The entire vegetative world, from the great forests to the humblest crop in the field, was suddenly struggling under a cold, dim sun. For medieval farmers, this was not an abstract climate anomaly, it was a direct assault on their survival. The consequences for agriculture were immediate and catastrophic. The data from the trees and ice was now speaking directly to the fields. Medieval agriculture was a high-stakes gamble with the seasons, and the staple crops that fed millions were not resilient. Wheat, barley, and rye, the foundation of the European diet, required a very specific and reliable timetable. They needed a frost-free spring for sowing and germination, a warm, sunny summer for growth and grain filling, and a dry, stable autumn for the critical harvest. The volcanic cooling shattered this delicate schedule. A late spring frost arriving after seeds had sprouted could wipe out an entire planting. A summer that was simply too cold meant the grains would never properly develop, producing shriveled, useless heads. Even a modest shortening of the growing period by just a few weeks could mean the difference between a full granary and an empty one. For a society already farming marginal lands, there was no buffer against such a shock. A single failed harvest would force communities to eat through their carefully stored seed grain, consuming the very resource needed for the next year's planting. This is where the tree ring evidence becomes chillingly personal. Researchers don't just see one narrow ring, a marker of one bad year. They see sequences of them 2, 3, or even 4 consecutive years of stunted growth. In the wooden Chronicles, this pattern is the undeniable signature of a multi-year agricultural collapse. The first cold summer depletes reserves, the second ensures there is no recovery. By the third, the system breaks. Local shortages balloon into regional famine as trade networks seize up, because every community is facing the same disaster simultaneously. The cold created a scarcity so profound it rewrote the rules of society. Yet the climatic assault was not one-dimensional. While the volcanic haze brought punishing cold to some regions, it also warped global weather patterns in other, equally devastating ways. The same atmospheric disruption that shortened summers could also redirect rain bands, delivering not a beneficial drizzle but relentless, torrential downpours. But the cold was only one half of the disaster. While volcanic haze chilled the continent, it also twisted the very mechanics of the weather, unleashing a second relentless foe. The same atmospheric disruption that shortened summers also trapped and redirected moisture-laden storm systems. What resulted was not a gentle, life-giving rain, but a catastrophic deluge. Historical chronicles from the spring of 1315 are unanimous and haunting in their description. They speak of a sky that seemed to have forgotten how to be clear, of rains that began in the planting season and simply never stopped. Fields transformed into shallow lakes, seeds rotted in the saturated earth, and the hope of a harvest dissolved into mud. For generations, these texts stood as a stark human memory of the calamity. But now, the natural archives provide the physical proof that this was not mere local bad luck, but a vast systemic climate failure. The trees once again hold a detailed record. In conditions of excessive wetness and warmth, A tree may grow rapidly, producing a ring that is wide, but that width is deceptive. Scientists can examine the cellular structure of the wood under a microscope. In a flood year, the cells are often larger, thinner-walled, and arranged in a chaotic pattern. They might even show specific anatomical scars, called flood rings or false rings, which form when growth is interrupted by oxygen starvation in waterlogged roots, only to resume later. A sequence of these wide, low-density rings in the historical record is a clear signal of prolonged, excessive rainfall. Simultaneously, the ice cores offer a polar perspective. In regions like Greenland, an unusually warm summer can cause surface snow to melt and then refreeze, creating distinct, glassy layers within the ice core. These melt layers are a direct indicator of abnormal warmth and precipitation events, even far from the drowned fields of Europe. When researchers align these proxy records, the flooded tree cells and the anomalous melt layers with the written cries of medieval chroniclers, the picture becomes terrifyingly coherent. The year 1315 was not just cold, it was profoundly, destructively wet. This was a compound climatic disaster. The volcanic eruptions had not simply turned down the global thermostat, they had broken the weather patterns themselves. A shortened, cooler growing season meant crops struggled to mature, while relentless rains ensured that whatever did grow was battered, molded, and impossible to harvest. The two forces worked in cruel synergy, creating a scenario where resilience was impossible. A community might prepare for a dry summer or a hard winter, but how does a society defend itself against a world that is both too cold and too wet, where the sun is dimmed and the sky is a constant, drowning gray? This was the precise environmental trap that snapped shut around medieval Europe. The catastrophe was not just a series of bad years, but a fundamental shift in the sky itself. To understand how a few volcanic eruptions could lock an entire continent into a cycle of misery, we must look beyond the initial blast and into the grand, rhythmic patterns of Earth's climate. One of the most powerful forces shaping European weather, even today, is a phenomenon known as the North Atlantic Oscillation. Think of it as a vast atmospheric seesaw, constantly tipping back and forth over the ocean. On one end is a permanent low-pressure system near Iceland, and on the other, a high-pressure system near the Azores Islands. The difference in pressure between these 2 points dictates where storms are steered. When the oscillation is in its positive phase with a strong pressure difference, it funnels mild, wet Atlantic winds directly into northern Europe, bringing relatively temperate and rainy winters. But when it flips into a negative phase, the pressure difference weakens. The jet stream, that river of air that guides our weather, becomes wobbly and meandering. This allows bitter Arctic air to spill southward, while storm systems stall and dump relentless precipitation over the continent. The result is precisely the kind of weather the Chronicles lament: cold, saturated winters that bled into dismal, sun-starved springs. This is where the natural archives performed another miracle of reconstruction. By analyzing the chemical signatures in ice cores and the specific growth patterns in trees sensitive to winter conditions, scientists can create proxy models, essentially best-guess historical maps, of the North Atlantic Oscillation's behavior centuries ago. What these models suggest for the early 1300s is startling. The evidence points to the oscillation becoming locked for years on end into a profoundly negative state. It was as if the volcanic eruptions had thrown a wrench into the gears of the Atlantic's weather machine, jamming it in the worst possible position. This discovery changes the entire narrative. A single volcano might cause 1 or 2 difficult years, but a persistently negative North Atlantic oscillation could amplify and prolong that shock into a relentless, decade-spanning ordeal. The initial cooling from the eruptions may have helped trigger this stalled pattern, which then became self-reinforcing, creating a feedback loop of misery. The famines were no longer just a consequence of cold summers. They were the product of a broken atmospheric regime that ensured every season was a trial. This elevation from a singular event to a sustained climatic pattern explains the terrifying persistence of the crisis. It wasn't just that the weather was bad, it was that the very rules of the climate had changed, leaving an entire civilization playing a game it could no longer win. This convergence of evidence from ice and wood gives us more than just a story. It provides a precise, unshakable timeline. One of the most profound achievements of this scientific detective work is a method called cross-dating. Think of it as history's ultimate fact-checking system. A single archive can suggest a possibility, but when two independent witnesses from opposite ends of the Earth tell the same story for the same year, the truth becomes undeniable. Here is how it works in practice. Deep within an ice core drilled from the Greenland ice sheet, scientists identify a sharp, dramatic spike in sulfate deposits, a chemical scream from a massive volcanic eruption. This layer can be counted year by year back from the present, giving it an absolute date. Thousands of miles away, in an ancient oak forest in Ireland or a preserved timber from a medieval English barn, dendrochronologists examine the tree rings. They find a sequence of brutally narrow, cold, stressed rings. By counting back from the known present, they assign a calendar year to that period of suffering. When the date of the volcanic sulfate spike in Greenland aligns perfectly with the first year of severe cooling in the European trees, the connection is locked in. We are no longer dealing with correlation. We have established causation with calendar year precision. This power to remove ambiguity is what transforms our understanding of history. Medieval chronicles might vaguely note a hard winter or a famine year, but two different chronicles from different regions could disagree on the sequence or even the year of events. The natural archives cut through that confusion. They provide a global, synchronous clock. The eruption of 1257 stands as the textbook example. Its sulfate signal in the ice is among the largest ever recorded, a stark line in the frozen stratigraphy. And when researchers look at tree ring collections from across the Northern Hemisphere, from the Alps to the Russian taiga, they find the same chilling signature beginning precisely in 1258, the growing season after the eruption. That event becomes an anchor point in time, a fixed pillar in the past. Every other layer in the ice and every other ring in the trees can be aligned against it. This is how we can state with confidence not just that the early 1300s were difficult, but exactly when the cascade began, how long each phase lasted, and how the relentless sequence of volcanic shocks and climatic lockdown piled one disaster upon another. With this impeccable timeline in hand, we can finally reconstruct the step-by-step collapse, watching as a changing sky methodically dismantled a civilization's ability to feed itself. The evidence converges into a relentless step-by-step narrative of collapse. It begins with a violent shudder from the Earth itself, a major volcanic eruption, perhaps the colossal Samalas event around 1257. The ice cores capture its chemical scream, a massive spike of sulfate aerosols injected high into the stratosphere. Within a year, that distant explosion becomes a local reality across the Northern Hemisphere. The tree rings record the consequence: narrow, dense bands of wood formed under a suddenly dim and cold sun. The first growing season after the eruption fails or yields a pitiful harvest. Communities eat into their carefully stored surplus, that crucial buffer against a single bad year. But this was only the opening act. The volcanic haze did more than cool the planet. It appears to have jammed the North Atlantic Oscillation into a deeply negative phase. This locked in a broken weather pattern for years, perhaps even decades. The proxy records show this clearly. It was not a one-year anomaly, but a sustained climatic regime shift. Winters became longer and brutally cold as Arctic air spilled freely southward. Springs turned miserably wet, with storm tracks stalled over the continent, delivering not gentle rain but relentless, drowning downpours. This is where the cascade accelerates. A second year of cold and saturated fields follows the first. Now the grain reserves are gone, consumed to survive the initial shortage. Farmers are forced to plant their precious seed grain into mud, watching it rot before it can sprout. The third year brings no reprieve. The negative oscillation holds firm, delivering another cycle of shortened summers and ceaseless rain. Harvests fail again completely. The crisis now moves from the fields to the barns and pastures. With no surplus grain to feed livestock through the winter, animals begin to perish. The death of plow oxen was a death sentence for future harvests, removing the very muscle needed to work the land. Sheep and cattle, sources of wool, milk, and meat, succumb to starvation and disease. Each element of the agricultural system, from seed to soil to beast, was under simultaneous and sustained attack. The tree rings and ice layers testify to this horrifying persistence. They show not 1 or 2 stressed years, but a sequence of 5, 6, 7 or more consecutive years of profound environmental stress. This is the core of the disaster. Recovery was rendered impossible. There was no breathing space, no good year to replenish stores, no season kind enough to rebuild herds. The climate itself had become the enemy, conducting a sustained assault that systematically dismantled every pillar of medieval food security. The human cost of this broken sky was about to be written not in ice or wood, but in the desperate choices of an entire civilization. The story of the broken sky was never confined to Europe's borders. While medieval chroniclers recorded the collapse of their own world, the silent archives of nature were capturing a planetary event. High in the White Mountains of California, some of Earth's oldest living residents, the ancient bristlecone pines, tell a parallel tale. Their gnarled wood, shaped over millennia, contains rings from the early 1300s that are strikingly narrow. This pattern speaks not of European damp, but of severe drought and cold stress in the heart of North America. Across the Pacific, in the high mountains of Asia, similar wooden chronicles from species like the Chilean juniper echo the same global refrain. Periods of intense cooling and climatic instability precisely aligned with the dates of the European famine. The trees were in agreement across continents, a chorus of distress recorded in wood. The ice cores provided the definitive global signature. Drilling projects in Antarctica, at the opposite pole from Greenland, recovered cores that contained the very same layers of volcanic sulfate. The chemical fingerprints from eruptions like Samalas were found in both the Arctic and the Antarctic ice, a clear testament to their truly global atmospheric reach. This was not a regional weather anomaly, it was a planet-wide climatic shock. The driving forces were unequivocally planetary, a series of volcanic events that altered the chemistry of the entire atmosphere. Yet, the human experience of this global shock was not uniform. In the arid landscapes of the American Southwest or the high steppes of Asia, the primary threat manifested as profound drought, a scarcity of water rather than an excess of cold rain. The impact on societies there was shaped by different forms of resilience, perhaps nomadic adaptations or sophisticated water management systems that European farmers lacked. This hemispheric perspective does something profound. It elevates the narrative from a tragic chapter in European history to a case study in global vulnerability. The proxy records from poles and forests worldwide act as a unified control experiment, proving the cause was external and immense. They show us that the medieval climate anomaly was a shared ordeal for the entire Northern Hemisphere, a reminder that when the sky changes, it changes for everyone. The real historical lesson lies in how each society, with its unique agricultural practices, food storage, and social structures, was prepared or tragically unprepared to weather the storm. But how do we move from seeing a chemical signature to feeling the actual chill of those lost summers? The ice cores hold a more intimate secret, a direct measure of the cold itself. locked within the very water molecules that fell as snow. This is the science of stable isotope analysis, and it transforms the ice from a simple archive into a precise, ancient thermometer. To understand it, think of water, H2O, as it evaporates from the ocean. Not all water molecules are identical. Most contain a common, lighter form of oxygen called oxygen-16. A much smaller fraction contain a heavier, rarer sibling, oxygen-18. When the ocean's surface is warm, evaporation is energetic, and water vapor readily carries away both the light and the heavy oxygen isotopes. But when the air is cold, the process becomes more selective. The heavier oxygen-18 molecules struggle to evaporate, preferring to stay behind in the liquid ocean. So, the snow that eventually falls on an ice sheet like Greenland, when global temperatures are lower, is inherently depleted in that heavier oxygen-18. The ratio of oxygen-18 to oxygen-16 in a layer of ice becomes a coded message about the temperature of the ocean at the time the snow originally formed. A lower ratio means a colder climate. By meticulously measuring this ratio down the entire length of an ice core, year by frozen year, scientists can reconstruct a continuous graph of past temperature trends. It is a quantitative record of the sky's mood. When researchers apply this technique to the Greenland ice cores from the late medieval period, the graph they produce is startling. It does not show a gentle, gradual cooling. Instead, it reveals a climate of sharp volatility, a jagged line plunging into deep troughs of cold. These pronounced dips align almost perfectly with the years identified in historical chronicles and tree rings as periods of extreme hardship and famine. One such dramatic temperature drop coincides with the catastrophic spring of 1315, that year of endless rain. The isotope data confirms it was not just wet, it was profoundly cold. This adds a crucial, measurable dimension to our story. We are no longer just interpreting growth patterns or chemical spikes. We are reading a direct temperature log. The volcanic sulfate layers tell us why the atmosphere changed. The tree rings show us the biological impact on forests and farms. And now, the oxygen isotopes tell us exactly how cold it got. This is the power of a multi-proxy reconstruction. Each natural witness has its own language and its own blind spots, but when their testimonies are woven together, they create a robust, three-dimensional picture of the past. The convergence is undeniable, a symphony of evidence all pointing to the same conclusion, that the medieval sky did not just turn unfavorable, it turned actively, measurably hostile. The cold and wet were not the only weapons in the sky's arsenal. While the volcanic haze plunged Europe into a chilling damp, other parts of the medieval world faced a starkly opposite threat, a relentless, desiccating drought. The same tree rings that recorded stunted growth from cold tell an equally vivid story when the enemy is a lack of rain. In fact, for detecting drought, these wooden archives are perhaps our most sensitive instruments. A tree struggling through a multi-year dry spell does not just produce a narrow ring, it produces an exceptionally narrow, almost pinched band of wood. The cells are tiny and densely packed, a desperate conservation of every last drop of moisture. Scientists can go even deeper, analyzing the chemical isotopes within the tree's cellulose. The ratio of heavy to light carbon atoms locked in the wood acts as a record of the tree's stress level, essentially measuring how hard it was gasping for water during photosynthesis. When these two lines of evidence converge, extremely narrow rings paired with stressed isotope signatures, they form an undeniable fingerprint of severe, prolonged drought. This precise fingerprint is found far from the flooded fields of medieval Europe. In the arid landscapes of the American Southwest, the ancient bristlecone pines and ponderosas tell a story of a monumental dry period in the 1300s, a time scholars now call the Great Drought or even the Mega Drought. For decades, these trees endured with barely a whisper of growth, their rings clinging to survival. This was not a brief dry spell, but a climatic regime that reshaped entire ecosystems and human societies. What is truly arresting for a historian of climate is the timeline. This profound drought in the Americas was unfolding concurrently with the famines and political upheavals across Eurasia. Different continents, different weather patterns, yet both caught in the grip of extreme climatic events during the same turbulent century. This global perspective is crucial. It prevents us from oversimplifying the medieval climate into a single story of cold and wet. The Proxies reveal a world experiencing a full spectrum of violent extremes. The driving forces, from volcanic activity to shifts in oceanic cycles like the Atlantic multidecadal oscillation, could simultaneously suppress rains in one region while funneling catastrophic precipitation into another. The medieval experience was not defined by one type of bad weather, but by a destabilized climate system capable of delivering whichever extreme was most devastating to a local way of life. Whether it was the drowning rains of Europe or the desiccating winds of the Southwest, human societies were left responding to crises not of their making, their fares written in the silent language of tree cellulose and polar ice. The natural archives gave us the why, the precise atmospheric mechanics of the crisis. But to understand the true scale of the catastrophe, we must turn from the sky to the soil, from climatology to the human landscape that received this shock. A cold, wet summer is a hardship, but it is not automatically a famine. The devastating difference lies in amplification, how the structures of a society can turn a climate event into a historic tragedy. The proxy data reveals the environmental trigger, while history and archaeology expose the loaded gun. Medieval Europe in the early 1300s was in many ways a civilization perfectly engineered for collapse when the weather broke. Generations of relative warmth and stability had encouraged a dramatic population expansion. People pushed cultivation into uplands with thin soil, drained marshes that were prone to re-flooding, and cleared forests that once acted as buffers. This placed an immense number of people on lands that were ecologically marginal, offering no resilience against a string of bad harvests. The margin for error had been erased. Furthermore, the feudal economic system created profound vulnerabilities. Grain storage was local, inefficient, and easily depleted. There were no national granaries or coordinated relief networks. A lord's responsibility was to his immediate tenants, not to strangers in the next valley. When local crops failed, the economic machinery to move food from areas of surplus to areas of deficit simply did not exist on the necessary scale. Trade was limited, slow, and expensive, often collapsing under the weight of universal scarcity. This lack of integration meant a crisis in one region could not be alleviated by plenty in another, because news traveled slowly, and every region was soon fighting the same battle against the sky. The social structure itself amplified the suffering. The peasant majority who worked the land were obligated to give a significant portion of their harvest to their lord as rent or tax, and another portion to the church as a tithe. In a good year, this left just enough to survive. In the first year of shortage, these obligations did not vanish. Farmers were forced to hand over grain they and their families desperately needed, consuming their seed stock and slaughtering their breeding livestock to meet demands or pay inflated prices for what little food remained. The tree rings tell us the climate shock was severe and sustained. Archaeology and manorial records reveal the social shockwave that followed, a cascade of failure where hunger led to debt, debt led to the loss of land and tools, and the loss of productive capacity guaranteed more hunger. The environmental crisis exposed every flaw in the human system. It was this fatal combination, a broken sky meeting a brittle society, that transformed difficult years into the years of famine. The natural archives show us the storm, but history shows us the house that was built without a foundation. The ultimate test for any scientific reconstruction of the past is a direct confrontation with the written record. Do the silent testimonies of ice and wood align with the voices of those who lived through the crisis? The year 1315 stands as the most harrowing example, a year seared into the memory of medieval Europe. Chroniclers from England to the Holy Roman Empire describe a spring of unending rain, fields turned to quagmires, and a harvest that simply did not happen. They wrote of a sky that wept without ceasing, a poetic but desperate observation. Now we can place those human words side by side with the physical evidence. The tree ring archives from that year across northern Europe do not show the narrow bands of a cold summer. Instead, they often show the opposite, wide rings with the chaotic cellular structure of a flood year. This matches the Chronicles perfectly, confirming the primary disaster was catastrophic wetness, not just cold. Simultaneously, the Greenland ice cores for that period show a pronounced melt layer, indicative of an unusually warm, wet air mass reaching even the high Arctic. The convergence is precise and powerful. The proxies validate the human experience, giving physical form to the chronicler's despair. They tell us the rain was not a local phenomenon, but part of a vast, anomalous weather pattern. But the relationship is not always one of simple confirmation. Sometimes it complicates and deepens the story. Take another difficult year like 1322, noted in some records for hardship. The ice cores for that period may not show a major, new volcanic sulfate spike. Does this invalidate the proxy method? Quite the opposite. It reveals the nuanced legacy of a broken climate system. A major eruption years prior could have already shifted the North Atlantic Oscillation into a negative phase that then persisted on its own, locking in patterns of cold and wet without a fresh volcanic trigger. The tree rings might still show stress from that entrenched pattern, a lingering chill in the growing season. This doesn't contradict history, it explains it. The written record tells us that people suffered in a given year. The natural archives explain the mechanism of that suffering, whether it was a new atmospheric shock or the ongoing echo of an old one. This partnership is what makes the story so compelling. The Chronicles provide the emotional truth, the immediacy of the crisis. The proxies provide the physical truth, the mechanics of the sky. One without the other gives us only half the picture. Together, they allow us to witness the 1300s not as a vague age of darkness, but as a specific, measurable, and understandable period where the environment turned against human enterprise. This validation transforms the famines from a legendary tragedy into a documented case study, one where every element of the disaster, from the global cause to the local impact, can be traced and understood. The eruption of 1257 left a scar across the entire planet's atmosphere. Ice cores from both poles show its sulfate signature is among the most dramatic of the last 10,000 years, a stark line of chemical evidence for a truly catastrophic event. The immediate climatic response, as recorded in tree rings worldwide, was exactly what science predicts. From the Alps to the Andes, the growth rings for 1258, and the following years are brutally narrow. These trees stood under a dimmed sun, their stunted wood a testament to a sudden volcanic winter. The summer cold snap must have been severe, and harvests across the Northern Hemisphere surely faltered. Yet here lies a profound historical puzzle. While those years were undoubtedly harsh, the epoch we remember as the Great Famine, the period of systemic collapse, did not begin until over half a century later, in the early 1300s. If the 1257 eruption was so colossal, why was there such a long lag before the full societal catastrophe unfolded? This gap between the climatic trigger and the human crisis is where the story becomes most revealing. It forces us to look beyond a simple cause and effect and into the complex interplay between a shocked environment and a society's capacity to absorb that shock. One compelling theory focuses on that very capacity for resilience. Medieval Europe in the mid-1300s, while vulnerable, still possessed certain buffers. Population pressure, though growing, had not yet pushed cultivation to its absolute limits. Communities likely still held reserves of seed and grain from previous good years. Social structures, while strained, were intact. The initial volcanic winter of 1258 would have been a terrible blow, but it may have been a blow that a still robust society could withstand, albeit with great suffering. It depleted those reserves, it stretched those social bonds, but it did not instantly shatter the system. The eruption was a massive quake, but the foundation, while cracked, held. This theory suggests the true disaster required not one quake, but a series of them. The 1257 event might be seen as the first and largest in a cluster of eruptions that followed in the late 1300s, a relentless battering that gave society no time to recover between assaults. The resilience that absorbed the first shock was utterly exhausted by the third or fourth. There is another, more subtle possibility. The 1257 eruption may not have just caused a few cold years. It might have initiated a longer-term shift in the planet's climatic baseline. As we explored earlier, such a massive injection of aerosols could have helped push key patterns like the North Atlantic Oscillation into a persistently negative phase. Think of it not as a single hammer blow, but as a hand shoving a heavy pendulum. The initial swing is the immediate cold, but the pendulum then continues to oscillate in a new, unfavorable rhythm for years or even decades. The tree ring and ice core data from the late 1300s show a climate of increased volatility, not just a one-time dip. The 1257 event may have been the shove that set this unstable, famine-prone regime into motion. It created a new normal of shortened growing seasons and erratic weather, a background state of stress upon which later volcanic shocks would compound. So the lag is not a mystery of inaction, but one of accumulation. The relationship between a volcanic eruption and a historical famine is rarely a simple straight line. It is a cascade where the environmental trigger interacts with pre-existing societal vulnerabilities, and where one shock can predispose the entire system to collapse under the next. The Great Famine was not the child of a single event, but the tragic heir to a chain of them, a chain whose first mighty link was forged in 1257. A single cataclysmic eruption makes for a dramatic story, but the truth etched into the ice is often more complex, and in some ways more terrifying. While the titanic event of 1257 certainly set the stage, the ice cores from Greenland and Antarctica reveal a subtler, more persistent pattern of violence in the decades that followed. Scattered throughout the layers corresponding to the late 1300s and early 1400s are not one, but several distinct sulfate spikes. These are the chemical signatures of what scientists call a volcanic cluster, a series of mid-sized eruptions occurring in relatively quick succession. Individually, none of these events may have matched the sheer power of the earlier mega-eruption, but their cumulative impact on an already stressed climate system could have been far more devastating. Think of it like recovering from a serious illness. One massive fever can knock you down, but with time and rest, the body can heal. Now imagine, just as you begin to regain your strength, you catch another cold, then another and another. Each new illness is milder on its own, but it prevents any real recovery, draining your reserves until the system is utterly exhausted. This is the chilling scenario the ice cores suggest for the medieval climate. A single large eruption creates a sharp, severe cooling that might last 2 or 3 years before the aerosols fall out of the stratosphere and the sun regains its strength. But if another eruption occurs just as the atmosphere is clearing, it injects a fresh pulse of sun-blocking particles, effectively resetting the clock on the volcanic winter. The cooling is not a brief shock, it becomes a sustained condition. The climate system is denied the chance to rebalance, locked in a prolonged state of atmospheric shock. This theory moves us beyond the search for a single smoking gun and into the reality of a climate under sustained assault. The tree ring evidence powerfully supports this nuanced picture. If the forcing was only from one mega eruption, we would expect to see a single dramatic dip in growth, those brutally narrow rings followed by a gradual return to normal width over the subsequent years as temperatures recovered. But what the oaks and pines often show for this period is different. They reveal a sustained suppression, a sequence of many narrow rings in a row, indicating not one isolated bad summer, but a decade or more where every summer was cooler than it should have been. The trees were not recovering because the sky was not clearing. The sun remained dimmed season after season by an invisible haze that was being constantly replenished. This creates a far more plausible engine for the prolonged agricultural failure that defines the Great Famine. A farmer might survive one or two failed harvests by eating seed grain and hoping for a rebound. But when the cold persists for 5, 6, or 7 years, hope itself becomes a scarce resource. The soil is never properly warmed, pests that would be killed by a hard frost survive in the muted cold, and the very knowledge of when to plant becomes obsolete because the seasons have lost their reliable rhythm. The volcanic cluster hypothesis provides that mechanism for persistence. It explains how the climate could remain broken for so long, transforming an acute crisis into a chronic one. This shifts our understanding of the forcing mechanisms from a simple one-time trigger to a cascading series of atmospheric injuries, each one preventing the healing of the last until the entire system of medieval life was pushed past its breaking point. The silent archives of ice and wood can tell us about temperature and rainfall, but what about the wheat in the field and the soil beneath it? To truly connect the climatic crisis to the dinner table, we must look for more direct agricultural evidence locked within the proxies themselves. This is where the science of archaeobotany enters the story. Archaeobotanists are like detectives of the ancient harvest, sifting through soil at medieval farm sites, mills, and even the bottoms of old grain storage pits. They recover tiny, preserved treasures, carbonized seeds, husks, and pollen grains. These fragile remains tell a specific story about what was being grown and, crucially, what was failing. In layers of soil dating to the famine years, researchers often find a shift in the types of crops represented. There might be evidence of a desperate turn towards hardier but less nutritious grains like rye or even famine foods like weeds and acorns, signs of a community scraping the bottom of the ecological barrel. This physical evidence of crop stress on the ground can be directly correlated with the stressful years recorded in the nearby tree rings, creating a powerful, localized link between a bad growing season and a hungry village. Beyond the seeds themselves, the proxy data allows for sophisticated modeling of past agricultural yields. Scientists can take the precise temperature and precipitation information derived from tree rings and ice cores and feed it into models of crop growth. By understanding how a specific variety of medieval wheat responds to a cold, wet June, these models can estimate with remarkable precision the percentage of harvest loss in a given year and region. It transforms the abstract idea of a cold summer into a quantifiable metric, a forecast of empty granaries. The story becomes even more detailed when we consider what was in the air. Ice core analysis goes beyond volcanic sulfates and temperature isotopes. It can also measure levels of atmospheric dust. Tiny mineral particles carried on the wind from continents away settle on the ice sheets and are preserved. A spike in dust in the atmospheric record can signal periods of intense drought and soil erosion in source regions like Asia or Africa, but it can also hint at local environmental breakdown. As the famine gripped Europe and desperate farmers abandoned fields, or as livestock died off and land management collapsed, exposed soils would have been vulnerable. Increased dust in later layers could reflect this tragic feedback loop, where climate stress led to poor land management, which in turn degraded the very soil needed for recovery, kicking up dust that further altered the atmosphere. This paints the most complete picture yet, a closed loop of cause and effect. The volcanic haze cooled the planet, the twisted weather patterns drowned the fields, failed harvests led to societal collapse and abandoned farms, and those eroded lands then whispered their own tale of loss into the global wind, a final signature of the crisis captured in the polar ice. Yet even the most eloquent witnesses have their blind spots. The story told by tree rings and ice cores is powerful, but it is not a perfect, unbroken record. To understand the past with true clarity, we must also listen for the gaps in their testimony, the places where nature's archives fall silent or speak in riddles. Take the humble tree ring. While it is a superb recorder of growing conditions, its message can be blurred by local noise. A narrow ring might signal a cold, wet summer, but it could also be the result of an insect infestation devouring the tree's leaves, a forest fire that scarred its trunk, or simply the intense competition for sunlight as the forest canopy thickened overhead. A scientist cannot look at one single tree and declare a climate event. The true picture only emerges from the chorus by comparing hundreds of trees across a landscape to filter out these personal stories of injury and rivalry and find the shared climatic signal that affected them all. The ice, for all its global reach, presents its own puzzles. A sulfate spike in a core drilled in central Greenland is a definitive record of a volcanic event in the atmosphere above Greenland. But was that event truly global? Or did the stratospheric winds simply funnel the volcanic plume over that one specific region? To confirm a worldwide climate-altering eruption, researchers need to find the same chemical signature in multiple ice cores from both polar regions, and often from high-altitude glaciers around the world. It is a painstaking process of cross-referencing frozen ledgers. Even the seemingly impeccable timeline has a subtle grain of uncertainty. Counting annual layers in ice cores is remarkably precise, but in periods of very low snowfall, years can become compressed and faint, introducing a potential margin of error of a year or two. Tree ring dating is extraordinarily accurate, but attaching a specific calendar year to a ring from a long-dead timber requires matching its pattern to a master chronology from living trees, a process that can sometimes hit a dead end in poorly documented periods. This is not a weakness of the science, but its essential strength. Honest climatology and history are built on acknowledging these limitations. The proxies do not give us a single, simple answer. They give us a range of probabilities and interpretations. A volcanic signal in one ice core is a clue. That same signal in 5 cores, aligned with narrow tree rings across 3 continents, becomes a case. The power lies in the convergence, in the careful, skeptical weaving together of multiple, imperfect lines of evidence. This nuanced understanding prevents us from making the past a caricature. It reminds us that we are not reading a history book written in stone, but piecing together a mosaic where some tiles are missing and others are slightly worn. The grand narrative of the medieval famines rests not on a single, flawless piece of data, but on the overwhelming weight of 1,000 fragments, all pointing in the same direction. This prolonged battering by the sky did more than cause a temporary crisis. It signaled a fundamental change in the world itself. The proxy records allow us to zoom out from the individual years of famine and see them within a much grander climatic narrative, one spanning centuries. The era preceding the famines is often referred to by scholars as the medieval warm period, or more accurately, the medieval climate anomaly. This was a time of generally milder, more stable conditions across the North Atlantic region from around the year 900 to 1250. Vineyards flourished in England, Norse settlers farmed Greenland, and harvests were relatively reliable. The tree ring chronologies from this long stretch tend to show consistently wider, healthier growth bands, while ice core isotopes suggest a warmer oceanic baseline. It was within this benevolent window that European society expanded, pushing its agricultural frontiers to their absolute limit. Then the regime shifted. The famines of the early 1300s did not occur in isolation. They mark the tumultuous, volatile opening chapter of a much colder and less predictable age, what we now call the Little Ice Age. This was not a single event, but a prolonged climatic phase that would grip the world with intermittent severity for roughly 500 years. When we look at the long-term trends compiled from thousands of tree ring series and the smoothed curves of ice core isotopes, the pattern is unmistakable. The graphs do not show a flat line that suddenly drops. They reveal a long, slow descent from the peak warmth of the medieval anomaly into a deeper, persistent chill. The slope of that descent is steepest right in the decades of the Great Famine. This period was the pivot point, the moment when the climate's long-term trajectory turned decisively downward. Think of it as a great ship slowly changing course. The initial turn is the most unstable, with the vessel rocking violently as it meets cross currents and new winds. The famine years were that violent rocking, the period of maximum vulnerability as the entire system transitioned from one stable state to another. The volcanic clusters acted as the storm that hit during this precarious maneuver, but the underlying instability was already there, built into the changing course of the climate itself. This framing changes how we understand the societal impact. A society can sometimes withstand a freak storm during a period of general calm. But when that storm hits during a period of inherent instability, when food systems are already stressed by a gradually cooling background climate, the consequences are multiplied. The gradual cooling meant growing seasons were slowly, imperceptibly shortening year after year, even before a major eruption. Grain varieties bred for the warmer medieval optimum were becoming less suited to their environment. The margin for error, already thin from population pressure, was being eroded not just by human expansion, but by a less generous sky. Then the volcanic shocks arrived, delivering a series of knockout blows to a system already weakened by this long-term shift. The famines were therefore the brutal intersection of two timelines, the slow, grinding pressure of a changing climate regime meeting the abrupt, catastrophic shocks of atmospheric violence. This is why recovery proved so elusive. The world they were trying to recover to no longer existed. The relatively warm, stable medieval climate was receding into the past, and a new, more demanding age was dawning. The silent archives tell us this was not merely bad luck, but a historical inflection point written in ice and wood, where human societies found themselves navigating the treacherous threshold between two very different worlds. The year 1315 is a name that echoes through history, a stark entry in the ledger of human hardship. To understand its true nature, we must place it under the lens of our assembled evidence, reconstructing the environmental engine that drove this legendary catastrophe. The ice cores from Greenland provide our first critical clue. In the layers corresponding to the years just before the famine, there is no single, colossal sulfate spike. Instead, we see the tail end of that earlier volcanic cluster, a lingering atmospheric haze from eruptions in the preceding decades. This background veil of aerosols had already cooled the global baseline, priming the climate system for instability. It was a sky waiting for a final push. That push came not from a new volcano, but from a locked and broken weather pattern. Reconstructions of the North Atlantic Oscillation for this period, derived from a blend of tree ring and ice core data, paint a decisive picture. The oscillation appears to have been stuck in an intensely negative phase for years on end. This meant the usual storm track was diverted, allowing polar air to dominate and trapping wet, low-pressure systems directly over Western and Central Europe. The tree rings from that continent offer irrefutable testimony to the result. From the oaks of Ireland to the pines of Germany, the growth patterns for 1315 are not just narrow, they are often abnormally wide with a chaotic cellular structure. This is the unmistakable signature of a flood year, not a drought. The trees were not starved for water, they were drowning in it. Now, listen to the human voices that describe the very same phenomenon. Chroniclers across England, France, and the Low Countries write of a spring where the rains began and simply never ceased. They speak of fields submerged, of seeds rotting in the ground, and of a summer that never knew warmth. The natural archives transform these poetic laments into physical data. The flooded tree rings confirm the relentless precipitation. The negative North Atlantic Oscillation reconstruction explains why the rains were so persistent and widespread. The residual volcanic haze in the atmosphere explains the accompanying chill that prevented evaporation and stunted any plant that struggled above the waterline. This is the environmental backbone of the disaster, a triple alliance of forces that made agricultural success impossible. The consequences unfolded with a terrible, predictable logic. With the spring planting ruined, there was no harvest in the autumn of 1315. Communities consumed their dwindling reserves. The following year, 1316, the proxies show the negative pattern held firm. The tree rings remain stressed, and the historical records note a second consecutive harvest failure. Now, true desperation set in. Seed grain was eaten, plow oxen were slaughtered for food, and the social fabric began to tear. By 1317, the third year of this climatic siege, the system broke. Prices for grain skyrocketed beyond reach, crime and unrest surged, and populations weakened by hunger became susceptible to illness. The historical narrative of social collapse is not a separate story. It is the direct human outcome of these environmental conditions, year after punishing year. The famines did not happen because of one bad storm, but because the entire sky for 3 years became an instrument of agricultural ruin. The silent testimony of the climate proxies raises a profound human question. If the trees and ice record a broken sky, where do we find the echo of broken communities? The environmental data acts as a powerful starting point, directing scientific inquiry toward the archaeological traces of the people who endured those harsh years. By aligning the precise timelines from tree rings and ice cores with evidence from the ground, researchers can trace the demographic shockwaves that rippled through medieval society. One clear signal comes from the very timbers used to build their world. Dendrochronologists often study the wooden beams in surviving medieval structures, barns, houses, and churches. By dating the tree rings in these beams, they can pinpoint the exact year the tree was felled. Across regions hit hardest by the famine years, a curious pattern emerges. There are noticeable gaps in construction, periods where few new buildings were started for a decade or more. This architectural silence speaks volumes. It suggests a society that had lost the surplus, the labor, and the stability required for building. When survival consumes every resource, grand projects are abandoned and maintenance falls away. The dated timbers become a proxy for societal vitality, and their absence aligns chillingly with the sequences of narrow, stressed rings in the climate record. Another line of evidence comes from a more intimate source, the resting places of medieval communities themselves. Bioarchaeologists can analyze the chemical isotopes preserved in human bones and teeth. The composition of these elements tells a story written in the body. For instance, ratios of certain nitrogen and carbon isotopes can reveal periods of severe nutritional stress or shifts in diet. A tooth which forms in childhood locks in a chemical record of those early years. When scientists examine remains from cemeteries dating to the early 1300s, they sometimes find isotopic signatures consistent with starvation or a desperate reliance on famine foods like wild plants or lower quality grain. These individuals carry the biological memory of the hunger in their very skeleton. Furthermore, the demographic profile of burial sites from this era can show subtle shifts. such as a higher proportion of remains showing signs of illness or growth interruptions among the young. This isn't about attributing single events to a specific cause, but about observing population-level trends that correlate with the prolonged environmental crisis. The climate proxies provide the when and the why for the atmospheric disaster. The archaeological and biological evidence reveals the so what the tangible human cost. A gap in church construction and a child's tooth showing nutritional stress are two different pieces of the same tragic puzzle. Together, they demonstrate how a climatic trigger, meticulously documented by nature's archives, initiates a cascade of investigation across disciplines. We move from measuring sulfates in ice to interpreting the silent stories in a beam of oak or a fragment of bone, each line of inquiry reinforcing the other. This convergence paints the fullest possible portrait of collapse, not as an abstract historical event, but as a lived experience that reshaped landscapes, halted construction, and left its mark on the generation that endured it. The data from the sky finds its answer in the soil, completing a circle of evidence that connects a changing atmosphere to the fate of a civilization. The climate proxies do more than map a blanket of disaster. They also reveal the subtle patterns of human resilience etched into the landscape. While the tree rings across northern Europe tell a story of synchronized suffering, a closer look at the data reveals fascinating pockets of variation. In some regions, particularly in sheltered valleys or areas with more diverse microclimates, the rings from the famine years are not as brutally narrow. They still show stress, but not the complete collapse seen elsewhere. These geographical refuges, hinted at in the wood, would have been places where some harvest, however meager, might have been coaxed from the earth. They become islands of relative stability in a sea of failure, potentially explaining why some communities in certain areas managed to hold on while others disintegrated. This unevenness in the environmental record forces us to consider the human choices that interacted with the climate. Societies were not passive victims of a uniform disaster. Their fate was also shaped by how they fed themselves. Consider the stark difference between a society deeply invested in grain agriculture and one built around pastoral herding. For the grain farmer, a cold, wet summer that rotted the wheat was an absolute catastrophe. Their entire annual cycle, their stored wealth, and their social structure were tied to that single, vulnerable harvest. But for a pastoral community on the fringes, perhaps in the highlands or the steppes, the calculus was different. While extreme cold could kill livestock, these societies were inherently more mobile. If one pasture was drowned, they could move their herds, their walking food supply, to another area. Their resilience was built on flexibility rather than fixed fields. The climatic volatility recorded in the proxies would have hit these two societies in profoundly different ways, creating a patchwork of survival across the medieval world. The archives even hint at adaptation within agricultural systems themselves. In some pollen records from lake sediments, scientists note a subtle increase in the evidence for hardier crops like rye or barley in layers dating to the crisis period, a possible shift away from more sensitive wheat. This is a biological signal of human ingenuity, a quiet adjustment to the new normal written in the landscape itself. So the story told by ice and wood is not one of universal doom. It is a nuanced map of pressure and response. The volcanic shocks and broken weather patterns set the stage, but the human experience of that stage varied dramatically. By reading these natural archives with an eye for difference, we begin to see the outlines of strategy and survival. We see where geography offered a shield, where economic choices provided a buffer, and where communities made difficult, pragmatic shifts to endure. The data reveals not just the force of the blow, but the varied strength of what it struck. This uneven landscape of impact would ultimately shape where recovery could first take root, and how the memories of this era guided future generations. Even with this powerful convergence of evidence, the story is far from complete. researchers stand at a fascinating frontier where each answered question seems to reveal a new, deeper puzzle. For instance, the ice cores clearly show multiple volcanic clusters throughout history, yet not every cluster triggered a famine on the scale of the medieval crisis. This begs a crucial question: what were the precise conditions that turned a climate shock into a civilizational collapse? The answer likely lies in a delicate balance of thresholds. Scientists are now working to quantify, with ever greater precision, the exact combination of temperature drop and precipitation change that would have pushed medieval agriculture past its breaking point. It is not just about how cold or how wet it got, but for how long and at which specific points in the growing season. A late spring frost is far more devastating than an early autumn one. A rainy June drowns seedlings, while a rainy August merely rots the harvest. Modern climate models, fed by the proxy data, are beginning to simulate these ancient growing seasons day by day, searching for those critical failure points. Beyond modeling, new laboratory techniques are allowing us to read the archives in ways once thought impossible. High-resolution laser ablation can vaporize tiny portions of a single tree ring, analyzing its chemical composition week by week across a single growing season. This could reveal not just that a summer was dry, but that a specific catastrophic drought struck in the crucial month of July. Similarly, scientists are now able to extract and analyze ancient plant DNA and pollen grains trapped within the ice cores themselves. This genetic material is a direct biological snapshot of what was growing and dying in regions thousands of miles from the ice sheet at the time the snow fell. It is like finding a pressed flower between the pages of a frozen diary. These advances remind us that our understanding is dynamic, constantly refined by new data. The medieval famines, once a vague historical tragedy, have become a precise laboratory for understanding the complex dialogue between a changing environment and human vulnerability. Every new technique sharpens the picture, turning broad strokes into fine detail. The core narrative of a broken sky triggering collapse is firmly established, but the subtle textures of that story, the specific whys and hows, are still being written in laboratories around the world. This ongoing quest transforms the past from a static fact into a living mystery, one that continues to teach us about resilience, fragility, and the profound ties that bind human fate to the natural world. This evidence rewrites the entire story of the medieval crisis. For centuries, the famines were framed as either divine punishment or the inevitable result of too many people on too little land, a simple Malthusian trap. But the natural archives force a fundamental revision. Tree rings and ice cores reveal these were not random acts of God, nor were they solely the product of human overreach. Instead, they were the tragic outcome of a precise and identifiable sequence. Specific, often global, climatic perturbations, primarily volcanism-driven cooling, and the associated atmospheric chaos it unleashed collided with a society that had expanded to the very edge of its resilience. This is the core of the new narrative. The cause was not a vague curse or a societal failing in isolation. It was a measurable environmental shock, a shock that traveled from the heart of an erupting volcano to the frozen stratosphere, and from there into the shortened summers and drowned fields of a vulnerable continent. The famines were the point of collision between a changing sky and a brittle way of life. This represents a profound shift in our understanding, from a purely historical explanation to a historical climatological one. We can no longer view these events through a single lens. The Chronicles give us the human cry of suffering, but the Proxies give us the reason for the pain. They show us that history is not made by people alone, nor by climate alone, but in the tense and often devastating dialogue between the two. This synthesis transforms the medieval years from a dark age of mystery into a documented case study, a warning written in ice and wood about the fragility of human systems when the natural world shifts its rules. This synthesis of natural archives and human chronicles does more than solve a medieval mystery. It fundamentally reorients how we view the past. For too long, history was seen as a stage where human ambition, conflict, and ingenuity played out against a static, passive backdrop of mountains and weather. The story of the famines shatters that illusion. It demonstrates that the environment is not a backdrop, but an active, dynamic character in the human drama, one that keeps its own meticulous diaries. By learning to read the language of ice and wood, we unlock an environmental history that runs parallel to our written records, sometimes confirming them, often complicating them, and always deepening our understanding. This forces a delicate but crucial reconsideration of two old historical debates, agency and determinism. Were medieval people simply victims of a climatic dice roll, their fate sealed by volcanoes they never knew existed? Or did their own choices, their expansion onto marginal lands, and their rigid social structures make the inevitable collapse so much worse? The Proxies suggest the answer lies in the collision, not the choice of one over the other. Human societies possess immense agency, but they exercise it within boundaries set by the natural world. The medieval expansion was a triumph of that agency, but it also narrowed those boundaries, raising the stakes until a shift in the sky could topple everything. This is not environmental determinism, it is environmental context. It acknowledges that while people make their own history, they do not make it under conditions of their own choosing. The conditions, as we now see, can change with terrifying speed, which brings us to a cautious, sobering parallel. Our modern global civilization is a masterpiece of complexity and interconnection, far beyond medieval imagining. Yet the core lesson from the Proxies remains starkly relevant. Complex societies are exquisitely sensitive to abrupt environmental change. Our food systems, though global, are built on similar assumptions of stability, predictable growing seasons, and reliable transport. The medieval case study shows us what happens when those assumptions fail, not for a season, but in a sustained, synchronous shock. It underscores that our security rests not just on economic or political systems, but on the stability of the very atmospheric and oceanic patterns we have begun to alter. This elevates the topic from a chapter in a history book to a timeless case study in the dialogue between human enterprise and the planetary system. It teaches us that resilience is not about building walls against the weather, but about building flexibility, diversity, and memory into the very fabric of our societies, so that when the sky writes its next unexpected chapter, we are not merely reading it as passive witnesses, but are prepared to write our own response. The journey from a historical mystery to a scientific explanation is now complete. We began with the haunting silence of medieval chronicles, their sparse words speaking of rain and ruin. We end with the eloquent data of tree rings and ice cores, nature's own forensic files. These archives did not just describe a tragedy, they diagnosed its cause. They revealed a world thrown into chaos by distant volcanic winters, a climate locked into patterns of relentless rainfall, and a fundamental regime shift that turned a warm medieval optimum into the volatile dawn of a colder age. The famines were not an act of divine wrath or simple overpopulation. They were the precise outcome of a climate system under violent stress, colliding with a society living at its ecological limit. This transforms our understanding of the medieval world, revealing it as a civilization exquisitely sensitive to the whispers and shouts of the global atmosphere. Its prosperity and its suffering were both written in the language of the sky, a language we have only now learned to fluently read. The true power of this discovery lies not just in solving an old puzzle, but in the method itself. These natural archives are essential tools, allowing us to write a history that is truer, more complete, and more humbling. They remind us that the past is not only recorded in parchment and stone, but in the very fabric of the living world. As we look at our own modern climate, with its vast networks of satellites and sensors creating a new kind of archive, we might pause to consider what future generations will read in our data. Will they see a society that learned from the fragile balance of the past, or one that failed to heed the warnings written in the rings of ancient trees and the deep, frozen layers of ice?